Welcome to the Explainer. Today, we are taking a microscopic look at industrial gas separation. We're going to really try to understand exactly how gas absorption works on a molecular level. And the best part, we're going to prove the theory using some actual real-world lab data that we gathered.
Okay, let's dive right into this. The big question we face is, how do chemical engineers actually capture and separate specific, completely invisible gases right out of the air? I mean, it's a super fascinating engineering challenge, right?
Section 1. What exactly is gas absorption?
Well, officially, it's defined as a unit operation where soluble components of a gas mixture are dissolved into a liquid phase. But simply put, we're basically taking a specific target from a big cloud of gas, forcing it across a molecular interface, and locking it down into a liquid. It's kind of like grabbing something out of thin air and trapping it in water. Now, right at that molecular interface, you've got two main types of diffusion that can happen. The first is equimolar counterdiffusion. Think of that like two components swapping places, moving in opposite directions. But for our separation technique, gas absorption, we specifically rely on the second mechanism, which is diffusion through a stagnant phase. This means only one component, our target gas, is diffusing one way through completely stagnant gas and liquid phases. And that actually brings us to a super crucial number, 1430. That is the Henry's law constant for carbon dioxide in water at 20 degrees Celsius. Now, because this value is so high, this specific process is heavily what we call liquid film controlling. What does that mean for us? Well, to boost the rate of absorption, we literally just need to increase the liquid velocity. Surprisingly enough, cranking up the gas velocity has very little effect. Moving on to Section 2, the lab experiment. To actually test this mechanism, we used a packed absorption column right in the lab. We started by filling up a sump tank with 40 liters of deionized water, and then we introduced an air and CO2 mixture. Then, over an 80-minute period, we collected liquid samples every 5 minutes. We analyzed those samples by titrating them with a 0.05 molar sodium hydroxide solution to find the exact concentration of dissolved CO2. Now for Section 3, analyzing the results. Now, what's really interesting about this raw data is that we tested two completely different gas feeds. We ran one with 9% CO2 and another with 16% CO2. And if you track the numbers, the 16% feed clearly results in a much higher concentration of dissolved CO2 right from the very start.
And this brilliantly illustrates the whole process in action. The absorption rate is incredibly fast initially. You can literally see how it shoots up because there's such a steep concentration gradient at the beginning. But eventually, that rate plateaus as it reaches equilibrium, basically when the water just can't physically hold any more gas.
So, the crucial scientific takeaways here are simple, but they're incredibly powerful. First up, mass transfer absolutely requires a concentration gradient. Second, a higher feed concentration, like our 16% mix, creates a much larger driving force. And finally, that larger driving force directly results in both faster absorption and a significantly higher final concentration of dissolved CO2.
Which brings us to a final kind of provocative thought to leave you with. If we can optimize these liquid flows and concentration gradients so effectively in a small lab setting, how efficiently could we scale this exact basic absorption mechanism to capture global carbon emissions? The engineering challenge is absolutely massive, for sure. But as we've seen today with our own data, the fundamental chemistry is proven. Thank you so much for joining me for this explainer, and stay curious.